So now that we've finished up our quadratic unit, we are going to move on to polynomial functions and looking at their graphs. This is going to be a pretty short unit. We'll probably be looking at a quiz or test here in about a week. So it's going to be a short unit on polynomials. Alright, to begin with, let's look at a graph of a function like y equals x. We all know y equals x is just a line that has a slope of 1 and a y-intercept of 0. So therefore it's a line that looks like this. Now, what we're going to be talking about here at the beginning is what we call end behavior. What's happening at the end of our graph? As it leaves the picture, what's going on? And we always put those arrows on our graph to show they're going to continue forever. So when we're talking about end behavior, we're simply talking about when you put the arrows on, what's happening? And so in this case, y equals x, we would say falls to the left and rises to the right, because as you go to the right side of our graph, as we go over here, our graph is going up. As you go over to the left side, it's going down. Just a simple concept where we're looking at different types of polynomials and what happens at the end of their graphs. So I'm going to sketch just some simple sketches of these. They're not necessarily going to be accurate. For y equals x squared, we should know our graph looks like that because it's going to be a parabola because it's x squared. And if you look at the end behavior of a parabola and how it differs from the end behavior on our linear function, both ends are the same. A quadratic function rises to the left and rises to the right. So when we compare those, you notice there's a difference there. The quadratic function leaves the screen in the same direction. Now, x cubed and x to the fourth we might not be familiar with quite yet, but you could graph those in your calculator. But to save time, we're just going to look at y equals x cubed as being very similar to a parabola on each side, except the negative side goes down. So therefore, when you look at the end behaviors here, again, we're leaving the screen falling to the left and rising to the right. And then finally our last one, x to the fourth, is going to look exactly like a parabola, except it's going to be even steeper yet than a cubic function, where it's going to look something like that. That's a rough sketch. And you notice x to the fourth, I'm going to circle this to make sure we don't get confused here. X to the fourth rises left and rises right. So when we're talking about the end behaviors of our graph, what's happening as the graph leaves our screen, hopefully you're making an observation about the exponents here. When we have an exponent of 1 and 3, the graph falls to the left and rises to the right. When you have an exponent of 2 and 4, our graph rose to both the left and the right. So what observation we can make there is any function that is of an even degree, in other words, the highest exponent is even, it's going to leave the screen up. Both left and right will rise. If you have an odd number as the highest exponent, your graph is going to go out opposite sides of the screen. It's going to fall to the left, rise to the right. And we've done enough graphs that it should make sense that if you put a negative number in front, it's going to flip your graph upside down. So if you were asked for the end behavior of these two functions I have at the bottom of the screen, y equals negative 3x cubed plus 2x minus 5, we don't care about the rest of this. When we're talking about end behavior, all we're concerned with is it's a cubic function with a negative in front of it. So we look at our cubic up here, it falls left, rises right. But a negative is going to flip that, so therefore that graph is going to rise left and fall to the right. It's going to look something like this. is going to be the general shape, where it rises on the left, falls on the right. We don't know what's happening in between. In here, we don't know what's happening yet. We're just talking about the end behavior of our graph. It's going to rise to the left, fall to the right. And then when we look at our second example, y equals 3x to the fourth plus 7, again, the plus 7 doesn't mean anything to us. It's got an even degree and a positive in front, so it's going to be the same as it was up there. It's going to rise to the left and rise to the right. So that's how we do end behavior. Our next step we're going to look at with polynomial functions is what happens in between then our end behaviors. And we're still going to stay away from some specifics. We're not going to get into exactly what a graph looks like yet. We're just going to talk about what could happen. And so if we think about our first example, y equals 2x plus 3, that's a linear function. And a linear function, we graph traditionally, just like we always have. But when you think about it, we're talking about zeros and turns in our graph. Therefore, we're just asking the number of them. Therefore, we're looking at how many times does this line hit the x-axis? Well, it's got 1, 0. It intersects the x-axis at 1 point. And then we're talking also about where does this graph turn? Well, a line never turns, so it has 0 turns. When we think about a quadratic function, our second example, y equals x squared minus 3x minus 1, I have no idea what the actual graph looks like. I'm just going to sketch a general parabola. I know this much about it. I know its end behavior. I know it's going to leave the screen going up, and I know it's going to be a parabola shape. So this graph could have 2 zeros, and now we can kind of see what we're talking about turns, where we change direction. Our graph was going down as we came in from left to right. Then it hit this point and it started going up. So it turned, it changed direction. So this graph had 1 turn in it. Now, it's important that we understand we're not finding how many zeros the function is guaranteed to have, how many turns it's guaranteed to have. We're saying that's the maximum number it could have. That's why we're using this word possible. It's possible for a quadratic to have up to 2 zeros. However, we've seen quadratic functions, parabolas that look like this, that have no zeros. So when we're talking about number of possible zeros and possible turns, it's important that you understand that. It's not saying this is what's going to happen in the graph. It's saying this is what could happen for a linear function. This is what could happen for a quadratic function. So to continue now our pattern on, as we look at this going forward, a cubic function, I don't want to go through all the work of having to graph all these, so I'm going to look for a pattern. A linear function could have 1 0. A quadratic function could have 2 zeros. Well, that would make sense then that a cubic function could have 3 zeros. And when we think about turns, a linear function can never turn. A quadratic function can have 1 turn in it. So therefore, a cubic function could have 2 turns in it. And so we could continue that pattern on. A quartic function could have 4 zeros and 3 turns. And a quintic function could have 5 zeros and 4 turns. All right. So what we're connecting with here is our exponent, our degree, tells us the number of zeros and turns a graph can have. If the degree 2, we can have 2 zeros and 1 turn. The number of zeros is always the same as the degree. The number of turns is always 1 less. So therefore, a quintic function, we said, could have 5 zeros and 4 turns. So those first two parts took some time to talk about, but they're not going to take you very long to actually do the work on. This last section on graphing polynomials using a calculator, I'm going to leave a lot of freedom to you here to understand this. I'm just going to walk through what is going to be asked of you. You're going to have to kind of play with this on your own and play with this in your calculator a little bit. So given a function like y equals 2x to the fourth minus x to the third minus 5x squared plus 2x minus 1. In order to graph that, we're going to want to find critical points. And those critical points are going to be our zeros, our maxes, and our mins. You've done all of this in your calculator before, so it shouldn't be too much of a problem for you to find this. I'm going to show you quickly what the graph looks like, and we're going to talk about relative max and relative min really briefly. So here's the picture you would see in your calculator if you type this equation in. And now I'm using a website here from Cool Math. I just kind of borrowed their graphing calculator for the purposes of something we could show. But when we're talking about relative max and relative min, what we're talking about is this point here is not the minimum value of the graph. The graph goes lower than that. However, it's a point where direction changes, and so we call that a relative minimum. Same thing here. This is called a relative maximum because it's not the highest point on the graph, but it's the highest point for that region. So when you're finding maxes and mins, this graph would have two minimum values, one maximum value, and two zeros. I'm going to leave that to you to find those on your calculator because you should be familiar with all of those commands. So what you're going to be expected to do is find all that information, zeros, maxes, and mins, plug them in to this information here, and then put those points on a graph and sketch a quality picture of that function. Alright, I know that got a little long. I apologize. Good luck, and if you have questions, make sure you ask.